Okay, so let's calculate some shadow prices based on a graphical method. So here we have the problems that we've previously considered. We'll start with the first one. The objective function here is 2x plus 5y. And so I've plotted the line 2x plus 5y equals 10, setting the right-hand side to some value. It's arbitrary really what you want to start out with. We're going to iteratively update it. But I'm starting out at 2 times 5, the product of the coefficients, just because it gives us a reasonable place to start in many cases. And then we have the constraints of the problem that I've plotted here. X plus 2y is less than or equal to 16 is the first constraint, but I've plotted greater than or equal to 16 because it helps to, when we're visualizing this, to plot the shaded area outside of the feasible region instead of inside it. So this is not changing the problem, it's just changing how we visualize it. The next constraint is 5x plus 3y is less than or equal to 45. I've plotted greater than or equal to 45. X is greater than 0 is the original. I plotted x is less than 0, and here is y is greater than 0, plotted as y is less than or equal to 0. So here's my feasible region in the white space, and it's a maximization problem, so I can keep on updating this number here, increasing it until I get to a place where the line has almost, it's just on the cusp of entirely leaving the feasible region. Clearly 41 is not okay, right? This line is constant values of the objective function. All the points on this line are have a value of the objective function equal to 41, but all of them are outside the feasible region, so this can't be correct. If I picked 39, well, then there's lots of points that are along this line that are inside the feasible region that have a value of 39, but it looks like I can go a little bit higher, right? I can move it up even further. It turns out 40 is the value of the objective function for which there's just 1 point left that's in the feasible region. It's on the cusp of leaving the feasible region entirely. That point is 0, 8. So x is equal to 0, 8 is equal, y is equal to 8 is the optimal value of the decision variables, and the corresponding value of the objective function is 40. So that solves the problem, but we want to do some sensitivity analysis. We want to see what is the effect of changing the right-hand side of the constraints on the optimal value of the objective function. What is the partial derivative of the objective function value with respect to changes in the right-hand side of each constraint? So in order to help us evaluate that, we're going to have to do a little bit of math. So I've got an Excel spreadsheet that I'm just going to use as a calculator. All I've done here now is put in the objective function coefficients 2 and 5 on x and y. And so this is telling me that my optimal values of the decision variables are x equals 0, y equals 8. I'm going to go ahead and plug those in. X is equal to 0, y is equal to 8. And let's see if the objective function value that I get by multiplying the x times its coefficient and add that to the y times its coefficient. Let's see if that gives me the value of 40 that I've determined graphically. So I'll do the sum product of these two and these two. Lock that. I'm not going to solve this using Solver. I'm just using this as a scratch pad, and it happens to have the same sort of format. This column is sort of like the x column. This column is sort of like the y column. So yeah, indeed, I get that value of 40 that I would expect from here. Then let's take a look first of all at our x plus 2 is less than or equal to 16 constraint. And so what we're trying to do is we're going to see, when I add 1 to the right-hand side of this constraint, how does that change the optimal value of the objective function? How much further can I bring up the objective function? Can I increase it by 1? It looks like I still haven't left the feasible region. Can I increase it by 2? It looks like I still can. Can I increase it by 3? Not quite. So it's somewhere between 2 and 3. So in order to find the perfect value, well, we know that this is going to be the optimal point, right? It looks like we can keep on sliding this up, and this is going to be the optimum. So let's find out what that is. That is 0, 8.5. So I'm going to have 0 and 8.5 are the values if I increase this constraint by 1. I can extend this cell down. That's going to evaluate the objective function for me at that point. So it looks like I have 40 plus 2.5. Zoom in. Yep, that's exactly right. Okay, so that is the optimal value of the objective function if I increase the right-hand side of this first constraint by 1. And that tells me that if there's, for every 1 increase in the right-hand side of this constraint, I get a corresponding 2.5 increase in the value of the objective function, then my shadow price is 2.5. Then you could ask questions like, well, what if I increase this by 3? How much is my objective function value going to change? I know that this is going to be a linear sort of thing. For every unit increase in the right-hand side of this constraint, I'm going to have a 2.5 increase on this objective value. So at this point, I can tell you, well, 2.5 is my shadow price. 3 is the change in the right-hand side of this constraint. So I'm going to be able to add 7.5 to the objective function. And that's the usefulness of the shadow cost, is it allows us to see or predict what effect changing the right-hand side of the constraint will have on the objective function or the optimal objective function value. So let's finish that up. I probably should have done this. I probably should have taken the difference between this value and this value, because this is how much it increased. Right? This was just representing the plus 2.5 there. So the shadow cost is 2.5. Let's take a look at this one here. This constraint, 5x plus 3y, is greater than or equal to 45. If I change the right-hand side of this constraint, plus 1, the objective function, the optimal value of the objective function is still 40. It hasn't changed because the optimal point is still here. Changing this constraint, the right-hand side of this constraint, doesn't affect the optimal solution. In fact, I could remove this constraint from the problem entirely, and that's not going to affect the optimal solution. This is related to the fact that this constraint here is not binding. The optimal point is not on that line. There is non-zero slack. There is a separation between this line and the optimal point. All right, let's take a look. So the I guess we can go ahead and plug in the numbers again. Well, 0, 8 is still the optimal values of the decision variables. Just copying that down, we've gotten optimal value of the objective function is still 40, and the difference between that and the original objective function value, I probably should lock this cell, is 0. So the shadow price for this constraint is 0. Let's take a look at this constraint, calculate the shadow price of that. If we add 1 to it, how does our objective function change, the optimal value of the objective change? Well, we can measure here. The point that we're at now is 7.5. That's now going to be the optimal point. We can kind of tell that we're going to have to move this line down. This black line corresponding to the objective function is outside the feasible region now. We're going to have to lower it a little bit, and we're going to get the optimal point, x and y, is 7.5. So let's go ahead and plug that in, 1 and 7.5. And then the optimal value of the objective function is 39.5. It changed by negative 0.5. And so I can tell you then that negative 0.5 is the shadow price. So when I change this by positive 1, I'm going to get a negative 0.5 of the objective function. And yep, it looks like right as expected. And let's do the shadow price on y. Let's zero everything out. If we add 1 to here, well, what's going to happen? This is still the optimal point. This is still our solution, 0, 8. And the optimal value of the objective function hasn't changed at all. 0 change, 0 shadow price. And that's again because this constraint here is not active. So when you turn in your submissions for the homework involving problems in which you're supposed to determine the shadow prices graphically, what I want you to do is, you don't need to show me your Excel spreadsheet, you just need to show me a picture. And so what that might look like, if I'm asking, if the question is what is the shadow price on this constraint here, then you determined using your Excel spreadsheet that the exact shadow price is plus 2.5, or excuse me, when we add 1 to this, we get a plus 2.5 increase in our objective function value. And I want you to just click on that point. And what you can do is take a screenshot of everything that's within this region, right? If you take a screenshot here, if I were to open this up, if you were to copy this into your document, I can tell that first of all, I can see all of your constraints, right? I can see that you've added 1 to the right-hand side of the constraint. I can see that you've added 2.5 to the objective function value by adding this plus 1 to the constraint. And that helps me see that 2.5 is the value of the shadow price.